let's consider a different scenario. Still, phase diagram A, B means binary phase diagram. And then we are considering two similar sized alloy. One is what? Pure A. The other one is gamma with CB gamma 0 labeled here. Okay? When I put these two pieces here, I said similar size, which means the total mass for each of them is similar. Join them, okay, at elevated temperature of T1 above the eutectoid temperature, okay. I still want you to plot the concentration profile. How would that concentration profile change for 0 time, finite time, and infinite time? Again, concentration profile C versus X, right? T equals 0, how would you draw it? Similar step function, right? Nothing happened. So on one side, I have 0 for pure A. Step up. Of course, what I draw is not steep enough, but let's say it's step up. And then constant, because the other side is just gamma at CB gamma 0. Make sense? That's your initial concentration profile. And then, if I'm going to ask to draw concentration profile at finite time, and for simplicity, I put the old one still here. How would you draw it here for finite time? Remember, we are in this condition. And of course, let's assume what? Read to yourself. Slow diffusion. Substitutional vacancy mechanism, slow diffusion, not like interstitial, very fast. Slow diffusion. And assume also what? Local equilibrium at the interface. What does that mean? It means right at the interface when two phases coexist, the composition for each of those phases would be determined by your phase diagram, by the intercept of the isothermal temperature line with your phase boundary. Then for finite T, how would you draw the concentration profile? Well, I draw it something like this. Here I'm within which phase? This gradual change, I'm within what phase? Alpha phase. I have change in composition continuously for long, okay? Because in here I'm in single phase, right? Single phase, I have how many degree of freedom? Other than temperature and pressure, I still have 1 degree of freedom, which is my composition, means it can change continuously, right? Far away, my concentration is still 0 because I start with pure A on this side. Make sense? Continuously change. And then what happened? I'm meeting the phase boundary or the interface, right? Between alpha and what's the other one? Gamma. Okay. Sharp jump. Jump to where? Jumped to the, what is the composition here? It's determined by, remember, the isothermal temperature with your phase boundary line, that intercept. Okay. And then jump to the other side, which is the gamma one. And then here I'm in what phase? Gamma phase. And still I have 1 degree of freedom, which means my concentration within this gamma phase can change independently and also continuously. But right at the interface, the composition for each of the phase are fixed. Make sense? Okay. And then let's say similar sized. What happens when T goes to infinity? Similar sized, pure A on one side, gamma on the other side. In the end, where am I going to be for the system? roughly similar size. I'm going to end up here, right? But it's in single phase, two-phase region. Two-phase region, which means, how are you going to draw it? I'm going to draw something like this. Does that make sense? Left side, I mean what? Single phase, what phase? Alpha phase. What's the composition for that alpha phase? Determined by the intercept, right? And what happens here? That's just the interface, right? And then I'm in the gamma phase, but now the gamma phase is this composition. Make sense? Completely uniform within gamma phase. But now these two phases coexist. Make sense? Now let's look at a similar scenario, but slightly different. We said we put a very large piece of A and a very small piece of gamma. A large piece of pure A, a small piece of gamma together. Similar assumption of what? Slow diffusion. Okay. But local equilibrium. Or put another, faster interfacial reaction, faster transformation going from alpha to gamma or gamma to alpha. Okay. Still, we want you to plot what? Concentration profile for different time. Okay. And then the first one, concentration with respect to location at T0. Simple, right? Step function starting from 0, step up, end up constant. And the concentration is Cb gamma 0. And then, how would you draw the concentration profile at a finite time t? Well, we said very large piece of alpha, very small piece of gamma. Which way would the interfacial phase move? Towards alpha or towards gamma? Which phase would it enlarge? Put another way. I have a big piece of alpha, tiny piece of gamma. Which way would that interface move? Move towards alpha, which means alpha shrink, or move towards gamma, which means gamma shrink? Gamma shrink, right? So I'm going to draw something like, for finite time t, I'm going to draw something like this. Of course, it's now drawn to scale. What happened? My interface moved towards the gamma one. Make sense? Move towards the gamma one. And at the same time, I have the so-called concentration at critical points. Here I'm in what phase? Alpha phase, gradual change in concentration, sudden change in concentration at the interface, and then gradual change again in gamma phase. Make sense? And the composition at the interface are still fixed by the intercept of the temperature line with phase boundary. Make sense? Then what happens when the time goes to infinity? We remember we said a very large piece of pure A, a small piece of gamma. In the end, where am I going to end up with? On this curve, on this line, where am I going to? Very close to here, to pure A. So how would you draw the concentration profile? Straight line, but where? At the bottom. Very good. So when the time goes to infinity, I'm going to have everything uniform, everything boring, homogeneous. That's kind of how you think, okay, to understand these types of behavior. Okay? And I think we have homework.